And as scientists head into the world of proteins, they're looking very closely at patients like Tony Ramos. Tony has cystic fibrosis, but it's not the typical case. CF almost always develops in early childhood. Tony didn't have any symptoms till she was 15.
I started having a cough, and then we kept thinking I was catching a lot of colds. And my stepmother thought, that's not right, so I started going to doctors trying to figure it out. And went through a lot of tests because I don't fit the profile. Tuberculosis, walking pneumonia, test after test.
At the time of her diagnosis, Tony's family was told she might not survive beyond her 21st birthday. She's now in her mid-40s. But her CF is worsening. 2 or 3 times a year, she does have to be admitted to the hospital to clean out her lungs.
Temperamental. They were always doing some little funky study to help the cause because we're not the normal, there's not a whole lot of us. I know that they don't know why, and it's the big question mark, and hopefully, research will keep going and figure it out.
Here's the question. Tony was born with a mistake in the same gene as baby Riley. And yet, for some reason, when Tony was a baby, she didn't get sick. Why? And now that she is sick, she hasn't died. Why? What does Tony have that the other CF patients don't have? Dr. Craig Gerard believes the answer lies in her genes, in her DNA.
How are you?
Good, how are you?
So, do you think the change in the antibiotics is helping you?
Yes.
Yeah?
And I dropped 4 pounds overnight.
That's a lot of weight.
Yeah.
Okay. Mind if I have a listen?
Nope.
No gene acts in isolation. It is always acting as a part of a larger picture. And there can therefore be other genes which compensate.
Could it be that Tony has some other genetic mutations, good mutations, that are producing good proteins that kept her healthy for 15 years and are keeping her alive right now?
You sound a lot better than you did when you came in. So I think you're on the mend. Okay, hang in there.
Thanks.
Bye.
Bye.
In my opinion, there are genes that are allowing her to have a more beneficial course, if you will, than another patient.
Good? Sound good. Okay.
Dr. Gerard is searching for the special ingredient in Tony. If it turns out she has 1 or 2 good proteins that are helping her, maybe we could bottle them and use them to help all CF patients like baby Riley.
Knowing that if there was ever an emergency and I didn't know how to do it and I couldn't get in touch with you.
No one can predict Riley's future or to what extent CF will affect his life. But now that we're getting the map of our genes, we'll be able to take the next big step. Because what genes do, basically, is they make proteins.
I get the sense that everybody's getting out of the gene business and suddenly going into this new business I hear about called the protein business. There's even a new name. Instead of the genome, I'm hearing this other name,
The proteome.
The proteome.
Yes.
What is that?
Well, the genome is the collection of all your genes and DNA. The proteome is the collection of all your proteins. See, what's happening is we're realizing that if we wanted to understand life, we had to start systematically at the bottom and get all the building blocks. The first building blocks are the DNA letters. From them, we can infer the genes. From the genes, we can infer the protein products that they make that do all the work of your cell. Then we've got to understand what each of those proteins does, what its shape is, how they interact with each other, and how they make kind of circuits and connections with each other. So in some sense, this is just the beginning of a very comprehensive, systematic program to understand all the components and how they all connect with each other.
All the components and how they connect. But how many components are there? How many genes and how many proteins do we have?
A real shock about the genome sequence was that we have so many fewer genes than we've been teaching our students. The official textbook answer is the human has 100,000 genes. Everybody's known that since the early 1980s. The only problem is it's not true. It turns out we only have 30,000 or so genes.
30,000 genes? That's it? Not everybody agrees with this number, but that's about as many as a mouse. Even a fruit fly has 14,000 genes.
That's really bothersome to many people, that we only have about twice as many genes as a fruit fly, because we really like to think of ourselves as a lot more than twice as complex.
Well,
as a
don't
fruit
you?
fly. I certainly like to think of myself that way. And so it raises two questions. Are we really more complex?
You show me the fruit fly that can compose like Mozart, and then I'll,
Yeah, well, show me the human that can fly, right? So we all have our talents, right?
I suppose we do, but as it happens, we have lots of genes that are virtually identical in us and fruit flies. But happily, our genes seem to do more. So let's say that I am a fruit fly. One of my fruit fly genes may make one and two slightly different proteins. But now I'm a human, and the very same gene in me might make one, two, three, four different proteins, and then these four proteins could combine and build even bigger and more proteins.
Turns out that the gene makes a message, but the message can be spliced up in different ways. And so a gene might make 3 proteins or 4 proteins, and then that protein can get modified. There could be other proteins that stick some phosphate group on it, or 2 phosphate groups. And in fact, all of these modifications to the proteins could make them function differently. So while you might only have, say, 30,000 genes, you could have 100,000 distinct proteins, and when you're done putting all the different modifications on them, there might be 1 million of them. Scary thought.
So starting with the same raw ingredients, the fruit fly goes, but the human, by somehow or other being able to arrange all the parts in many different ways, can produce melodies, perhaps.
Yes, although we're not that good at hearing the melodies yet. One of the exciting things about reading the genome sequence now is we're getting a glimpse at that complexity of the parts and how it's a symphony rather than a simple tune. But it's not that easy to just read the sheet music there and hear the symphony that's coming out of it.
Okay, so it's not just the number of genes, it's all the different proteins they can make and then the way those proteins interact. And to figure out all those interactions and how they affect health and disease, that's going to keep scientists very busy for the next few decades.